This video is for ELEC 1510 Logic Design. This is Lecture 24, Video 2 on Read-Only Memory, or ROM, corresponding to textbook section 7.5. ROM devices are slightly similar to RAM devices, except that they're missing the write operation. So read-only memory means it's a memory unit that you can only read from. And in general, what a ROM is a type of memory that is configured at the time that it's built and then can never be written to again. So when you build the device, you also program in the ones and zeros, and then it can never be written to again, unlike RAM, which can be written to again. So you may be familiar with certain types of ROM, like for example CD-ROM was pretty widely used until probably like 2005, 2010-ish, when streaming started to sort of supplant CD-ROMs as a means of getting information out to people. So rather than buying like a CD-ROM with information on it, you now most of the time stream information. So I wouldn't be surprised if ROM gets phased out over the coming decades. There are still types of ROMs like Blu-ray discs that are still used because the quality is much higher than anything that you could get through streaming. But as the quality of streaming catches up with the quality of ROM, you'll see it eventually get phased out. So here are some things about ROM as opposed to RAM. ROM is programmed at development time and can't be changed. And as I mentioned, there is no write operation for ROM. It's read-only memory. It's just meant to be read. Okay, so a ROM schematic in general is going to look something like this, and it's very similar to the structure of the programmable logic array that was shown in the previous video. You have address lines, I0 through I4, in this case for 5 address lines, a 5x32 decoder that's going to give you 32 addresses of information. And then there are 8 bits, so there are 8 output lines. Now each output line has an OR gate that's a column connected to all possible address lines. Now let's say, for example, that I input address 0, 0, 0, 0, 0. Now this line is going to get driven high, which means any connection that's formed between the horizontal row for the address and the vertical columns for the outputs are going to be ones. So let's say I put a 1 there, a 1 here, and 1 here. Now my output will be 1, 0, 0, 1, 0, 0, 1, 1. So that's essentially the information stored at the very lowest address. And it's stored through the connections made between the columns and the rows. Now, realistically, it would probably make sense to have a 0 as the input as well to all of these OR gates, just to make sure that if there's no connection formed between anything, they don't output noise, or basically randomness. You want to make sure that they're actually going to output a 0 if there's nothing connected. So now let's say that I input address 0, 1, 1, 1, 1. That's going to be address 30, which means that whichever lines are connected here are going to show up at the output. So let's create some connections there. So now the data that's given at the output is going to be 1, 0, 1, 0, 0, 1, 0, 1. Again, the connections form the data that's given at the output. So if you want to stream data out, you would just form all of the connections for every byte of data that you need, and then run through all possible addresses, and the data would be streamed out sequentially. Now in general, you would be given a ROM truth table for a whole bunch of data. In this case, we again have 5 address bits and 8 data bits. And so each address is going to correspond to 8 data bits, For example, address 0 is going to correspond to the very top row here, 10110110. This data is basically arbitrary at this point. And so what happens is every time there's a 1 in the truth table, you form a connection between a column and a row, or basically in the same way that a programmable logic array was developed, you don't destroy the fuse that was originally there between the column and the row. Anytime that there's a 0, you don't want a connection, which means that there was a fuse there originally, and you want to apply high voltage to destroy that fuse to get rid of the connection. So this truth table can be directly implemented as a ROM by creating connections that correspond to the 1s and 0s in the row shown in the previous slide. So again, for the very first row, we had 10110110. So we create connections wherever there's a 1. So here there's a connection, 1, 0, connections here, 1, 1, no connection, so that's 0, 1, 1, 0, which matches the data shown in the previous slide. And then for the rest of the rows, we just create all of the data there. There's only ever one row selected at a time by using the address select lines, and then that data is given at the output. So this then is how ROMs are developed using logic circuits. So this is the type of ROM that you would see on a little integrated circuit chip that would be used in a microsystem. However, other types of ROMs, like CD-ROMs, are obviously pretty different. Those have to do with optically coating the bits on the surface of plastic by using laser reflections. So this basic principle would apply to all ROMs, but the actual logic circuitry that we've explained here really is only relevant to integrated circuit ROMs.